Okay, so I'm going to be talking about topics 5 through 12 from my own problem set. And so this first one looks at topic 8, which is external flow. And so we want to find the drag if this is L at the adjacent edge from the leading edge X. So the drag force. And so we assume that this is steady state, constant density, the weight of air is negligible, pressure forces cancel, and that the material of the brick chimney is concrete, meaning that the surface is rough. And so when you have a rough surface with turbulent flow, the rough surface dominates the CF value. And so we need to see what type of flow we have and if that situation would apply. And so using the Reynolds number at L, we can plug in the velocity, the distance from the leading edge, and the dynamic viscosity of air, and we get that this value is greater than 10 to the 6th, meaning that this flow is fully turbulent. And so for fully turbulent flow, over a flat plate, the CF value is equal to this equation here. And so we can plug in the epsilon value for concrete, and then the distance from the leading edge, and we get this value, and then we can plug that CF into this drag force equation, and then that's how you get the drag force. Okay, for question 2, this is topic 5 and 6, laminar and turbulent. So there's an oil pan here with some piping with multiple bends and a centrifugal pump. And so we're going to have to use net positive suction head, topic 6, and then internal flow, topic 5, to solve this. And we want to know the pressure at point 1, which is down here, for both laminar and turbulent flow, because we have 2 different diameters for the pipe, and so the Reynolds numbers are going to be different. So first we have to decide what type of flow we have for each diameter, and for the smaller diameter we have laminar flow, and for the larger diameter we have turbulent flow, using this equation for Reynolds number. And then if we start by finding the pressure for the laminar flow equation, we use the F prime equation for specifically laminar flow, and we get this value. And then we have to find the total head loss, which is equal to the script F, the friction coefficient, and then plus the sum of the minor losses, which comes from the bends, and the K value was given. And so we just plug all of that in and get this value. And then to find the pressure at point 1, we use extended Bernoulli equation. And so this L, HL, is the total, and it's really like F over G total. We know that Z1 is 0, and then it was assumed that V1 is much less than V2 because the areas are much different, and so V1 is 0. And then we know that net positive suction head is equal to this equation here, and if the right side of the equation is the suction point, then we can rearrange this by subtracting Psat over rho g and get this equation in terms of net positive suction head, because that's a value that we have. And so by doing that, we can solve for the pressure at point 1, which is this equation. Then we plug everything in for the laminar flow, and this is what we get. And then you do the same exact thing for the other Reynolds number, but the F prime equation is just a little bit different because this is turbulent flow, and this epsilon is for the rubber tubing, the surface roughness, and then you just plug everything in and do everything the same, and this is the pressure that you get if you have the much larger diameter. Okay, number 3, this is flow through porous media. We're going to be looking at the minimum fluidization velocity and the Ergon equation. So we can assume that this is a vertical system, there's an upward gas flow, and that it is a confined system because you have Sandman punching Spider-Man. And you can think of his arm as being porous sand. And so if we wanted to find the minimum fluidization velocity to get his solid arm to act more like a fluid, then we can use this equation. Everything in here is known except for the BS part. And so you can plug all of those in to get the constants in front of there, and then you can use like a calculator to solve for this, or you can use the quadratic formula to get to solve for the polynomial, and this is the value you get. And then if we wanted to find the friction at the minimum fluidization velocity, we could use the ergon equation right here and just plug in the velocity that we just found into this equation, and this is what we get. Okay, now for question 4, this is topics 10 through 12. And we have this boat moving over a liquid methane lake on Saturn's moon Titan, and the bottom plate is stationary, but the boat is acting as a top plate that's moving at a velocity u. And so we want to know what the velocity profile is going to look like. We can assume that liquid methane is incompressible and it is a Newtonian fluid, and that the fluid moves in the positive x direction so that Vy and Vz are 0, and that the boat is wide relative to the depth. So Vx is not a function of z. This is shear driven flow, gravity acts vertically downwards, steady state, no electric field, no slip of the walls, and that it is laminar flow. So first, we need to do Navier-Stokes equations. And then this is our continuity equation, and everything in here is 0 based on these assumptions. And so we find that dVx dx is equal to 0. And then if we do an x-directed Navier-Stokes equation in the direction of the fluid flow, we have it written out here. We know that from our assumptions, continuity tells us that this is 0, and the second derivatives are 0. Steady state, this is one-dimensional flow. Gravity acts vertically downwards and not a function of z, and so we get the second, or d2 dx dy 2 is equal to 0. Okay, and then if we integrate twice, we get this equation with two constants, and we have to apply our boundary conditions in order to solve for that. And so our first boundary condition is no slip at the walls. So at y equals 0, the very bottom, there is no velocity because it's stationary. And then at the top, where y equals h, the boat is moving, and so the velocity is equal to u. And we can plug those all in, and we get that our velocity profile is equal to this. This is our numerical velocity profile. And so if we wanted to turn this into the numerical velocity profile, we wanted to go back to what we got from Navier-Stokes equation, the second derivative, and we just apply the rules for that. And this is what we get for the velocity at any node n analytically. And so if you plug this all into Excel, those two equations I just showed you, you can find the velocity at any point y, and this is our velocity profile. You see that it varies linearly with, the velocity varies linearly with a change in height. And so this question wanted to know halfway there, and you get 6.5 as your answer. And then, yes, that is it. Okay. For this last question, we're going to look at topic 9, which is compressible flow, and we're going to look at choked flow. So you have this car tire with a hole in it, and so it's acting like a converging nozzle because it's going from a large area to a smaller area. We can assume that air is compressible in an ideal gas. The system behaves like a converging nozzle. The upstream pressure is constant and stagnant. The inlet velocity is negligible, and the process is isentropic, steady, and one-dimensional. So from table A-13 for values, so we want to look at choked flow, and so this means that the Mach number is equal to 1, and if we want values for the stagnation property, since the inlet velocity is 0, we can use A-13 at a value of Mach 1 to find the critical properties like the question wants, because we know the stagnation properties, and so you use these equations, multiply it over, and then that's what you get. And then if you wanted to know the velocity at the exit, you would use this equation for stagnation, and then this is your outlet temperature, which was given, and then That's all you have to do. And thank you for listening.